to the best of our knowledge. Now, one of the most important facts, of course, in astronomy is that the speed of light is a constant. And that means the further we're looking away, the further back in time, we're also probing. So astronomers are also historians in that sense. And so as we move away from the Earth now, we'll begin to discuss our distances in terms of light seconds first, so just beyond the moon, and then light hours, light days, light years, and so forth. So our goal in our research program is really to understand where the structures you're seeing, both from planetary systems to stellar systems and star clusters, to the galaxies themselves and the black holes within the galaxies, where these structures come from, where do they arise in the universe and how. So now about 100 light years away from the Earth, and the galactic disk about 100,000 light years across. The nearest big galaxy about 1 million light years away, Andromeda. And as you know, the universe started about 14 billion years ago, so the furthest we can see in principle in our horizon is 14 billion light years. And most distant galaxies actually probe pretty close to that limit. So we've actually seen objects within about 90% of the volume we in principle can see. Then we know the Big Bang occurred, of course, because it's glowing radiation that's left over has been detected for many years now, the microwave background, which you're seeing in this color around us. Okay, so from studies of cosmology and basically the large scale, the universe, we actually know now that the normal matter that makes up ourselves, our planet, our star, is actually only 4% of the total. And these unknown quantities, which make up 96%, have just been given names dark matter and dark energy. Dark matter we know because of its gravitational influence, and dark energy because it's accelerating the expansion of the universe. So very early on, the universe was very hot and very high temperatures. We actually now know that the forces that we control matter today, so like gravity, but then also the strong nuclear force, the electromagnetic forces that control electric charges, the weak nuclear force that mediates radioactivity, then gravity. These four forces we think were closer together. So certainly the electroweak theory has been established to unify these two forces. We think the strong force is also joined in the so-called grand unified theories, or GUTS. But it's sort of a holy grail of physics for the theory of everything, the toe here, which would probably have to involve linking quantum gravity, development of such a theory very early on. In any case, today it's gravity that is, on large scales, is basically dominant. There's no antimatter, so there's there's no anti-gravity that's resisting, cancelling out gravity as occurs for electromagnetic charges, positive and negative charges. So that means over long distances, gravity is the long-range force of interest. And it is pulling structures together to form various objects. So things are collapsing because of gravity, and that collapse then can be stopped by various things. So rotation, so angular momentum. So in some sense, that is stopping all the material falling to the center of our galaxy, the Milky Way, because we're orbiting around. We have angular momentum, just as the Earth going around the sun has angular momentum, so stops it falling into the sun. But there are star clusters, like globular clusters, that have stars orbiting around. The angular momentum of their orbits is also preventing the collapse at this point. And whole galaxies, even elliptical galaxies. So you can have angular momentum stopping things even when it's not pure simple rotation like in our disk galaxy. Then other forces that can stop collapse include pressure. So that can be simple pressure, like gas pressure. So a hot gas has more pressure than a cold gas. It's hotter in the center of the sun than in the outside, and so there's pressure supporting the sun. So the sun, in fact, is partly supported by gas pressure, partly supported by radiation pressure. So that's the photon pressure, because there are more photons in the center of the sun than outside. So there's a balance then between this pressure and gravity stopping the sun from collapsing further. And then there's another kind of pressure called degeneracy pressure. It involves quantum mechanical effects. So the fact that you cannot put two electrons in the same quantum state, at least not very easily, allows certain structures like white dwarfs to stop collapsing. And then not to put protons and neutrons in the same quantum state allows neutron stars to exist. And then a related quantum state pressure, degeneracy pressure, is also supporting planets. It stops them collapsing. So these are the outcomes of collapse, then stopped at some point by various things here, galaxy, stars, and planets. Now, if, of course, gravity can become strong enough, it can overwhelm those pressure forces, and in that case, collapse continues to basically, we think, an unlimited state, a singularity hidden inside an event horizon, and that's known as a black hole, which, of course, has now recently been imaged, at least the shadow of that event horizon around the radioplasma by the Event Horizon Telescope in 2019. So black holes certainly exist. Now, the processes that are doing this support, you can think of these stars and galaxies as being almost in equilibrium, near equilibrium. So they're relatively simple structures. So the sun is relatively simple and can be described by quite simple equations. So we understand how the sun is working pretty well. The processes we're actually studying in the group relate to how objects form. And in that case, things get more complicated. So we still have gravity pulling stuff together. That pull can be resisted by different things like rotation and pressure. But there's all other kinds of things, magnetic fields, but also explosions like supernovae occurring in the interstellar medium. And so the processes we're working on, galaxy, star, and planet formation from gas, either between the galaxies or in the galaxy, these are non-equilibrium processes, and that means they're more complicated. Now, physical structure then is arising because of this fight between gravity and these different processes, but also chemistry is becoming more complex in the universe. So as you probably know, there are different chemical elements. The simplest is hydrogen with just one proton in its nucleus. Here's helium, 2 protons. But then basically all the chemical elements are just determined by the number of protons in the nucleus. And most of these elements are cooked up by nuclear fusion in the centers of stars and then returned to space in, say, exploding supernovae or exploding type 1a supernovae, which are exploding white dwarfs. There's some coming from merging neutron stars as well. But so most elements in the periodic table are produced in these processes. And so the chemical complexity of the universe increases over time as the stars are born and live their lives and then die. Now, amongst these chemical elements, most is still hydrogen. So about 75% is hydrogen, about 24% is helium. So there's only about 1% of everything else, 1 or 2%, at least around where we are in our galaxy. Of that 2% in these other heavy elements, about half of it is locked up in small dust grains containing carbon and silicon and oxygen, little particles of smoke or soot. You can think of them like that. And these are very important, these dust grains, because these provide surfaces in space where other molecules and atoms can land. So hydrogen is one example, but also water ice can form on these dust grains when it's cold enough. And in fact, quite complicated molecules can form in space, catalyzed by these dust grains. So up until, this is fairly recent, within the last few years, but there's about 200 molecules and molecular ions that have been found in space. So here listed 2 atoms, 3 atoms, all the way up to more than 12 atoms here. And these include things which are biologically interesting, like some amino acids, and particularly glycine, the simplest amino acid, has been claimed, although it's not yet certain. If you open a meteorite that comes to the Earth, you in fact find all the biological amino acids that we use, about 20 of them, and more are found in meteorites. So chemistry is very important, we think, in space in producing prebiotic conditions, molecules that allow life to arise. Okay, now because of this complexity, there are many open questions in our research fields. This is what keeps us busy. So we're interested in what sets the rate of star formation in galaxies. How do star clusters form? Most stars form in clusters. Half of stellar systems are binaries. That's 2 stars together. We're interested in that. We don't really know why that is. Stars have a range of masses. So the most massive can be about 100 or even 200 times the mass of our sun. But most stars are quite low mass. So why that is and how do the most massive stars form is an open question. The very first stars to form in the universe, we don't know what they were like, and we would like to know that. And in fact, there may be a deep connection between these first stars and how the big black holes in the centers of galaxies, the supermassive black holes, form. In terms of planetary systems, we know there are many out there, but we don't really know how exactly they come into being, how they form and grow. And then, of course, some big questions. How did life originate on the Earth? How special is our solar system? And is there life out there in the universe? So to tackle these complicated problems, what we do in our research group is 3 main things here. So we're developing theoretical models using equations. So you can call that analytic theory, when typically we're solving an equilibrium. So we might balance gravity against thermal pressure, for example, and there's an equation that describes that. So we try and come up with theories and equations that solve some subset of this problem. When it's too complicated, we use numerical simulations on big computers to do numerical simulations. And then, because these are complicated theories and simulations, we need to test them against lots of observations. So we do a lot of observational work. So first, some theoretical work that we've been doing over the years. My first project when I was doing my PhD was to work on a theory for how stars form in galactic disks. So many galaxies are like the Milky Way, are rotating systems supported by angular momentum. But what are the processes that actually control star formation in here? So this was a theory that actually related star formation to a process of cloud collision. These little red dots are meant to represent clouds which orbit around in the disk and occasionally bang into each other and trigger star cluster formation. Now, individual stars form, we think, from dense gas cores in space, and there's been a lot of work over the years, and we have focused on analytic work extending this to high mass stars. So the sequence is shown here. You have a dense gas core, it collapses, it's partly supported by angular momentum, which forms a disk, but there's also magnetic fields in here, and the magnetic fields spin and actually make these outflows, which then blow back part of the gas core and eventually leave behind a star with a disk. These are the magnetic fields, and maybe planets then form from this disk. We've extended this to then develop a theory for planet formation in these disks. We call this inside-out planet formation. We'll mention this briefly at the end. And then more recently, we've been working on a theory for the origin of black holes in the very, very early universe. Okay, often these theories are limited because the equations are too complicated to solve when you have all of these processes. So then we resort to numerical simulation. And the idea here is to split up the volume of space into a grid. So here just shown in 2 dimensions, but normally we would work in 3 dimensions, of course. So each cell here represents a little piece of space, and there are certain conditions of the gas, density and temperature, radiation field, magnetic fields can be followed, the chemistry would be followed in one of these cells, and there can be flow of gas between the cells, and there can be flow of radiation. So there are equations being solved from cell to cell to understand how the system would evolve, and then these are put onto big computers to solve the problem. So here's an example of a numerical simulation of a galactic disk, which was actually designed to test this analytic theory. So it took us maybe first 10 years, maybe 18 years to get this up and running to do this test. But what you're seeing here is a movie that runs over a few 100 million years. It'll loop back now in a second. Let's play again. So this is actually running for about 100 million years. And at this point, the galactic disk, the gas, is fragmented into many clouds. So each of these might be 1 million times the mass of the sun orbiting around. You notice the ones in the inner galaxy, they orbit around more quickly. They complete a rotation more quickly than if you're in the outer disk, where it takes longer, obviously, to go around. And because of that shear, we say, so those things move faster in the inside compared to the outside. If you look closely, this cloud will actually collide with another more slowly moving cloud. And so it's that process of shear, different velocities at different radii, setting the cloud collision process, which is one of the predictions of this theory. So then this is a big simulation of a few, several tens of thousands of parsecs or light years across the galaxy. Here we zoom into a little patch and we try and follow to smaller scales. The computers are limited at some level, so if you want to really see the fine detail, you have to zoom in. And other simulations that we do are more idealized. So this, we might do experiments. You can think of them as, so here are 2 molecular clouds, giant molecular clouds, which are magnetized and turbulent. And the process here we are studying is when they're on their own. So these 2 spherical clouds they have some internal motions. Gravity begins to operate. We get filaments, but the collapse is not particularly ordered, and there's only a small fraction of the gas becomes very dense here. Now, this case on the right is when we ram the 2 clouds together, they are colliding, and that's the process that we think may trigger star cluster formation by compressing the gas into a small region. So this is more efficient at forming stars here. And if we look in detail at the kinds of structures that arise in the simulations, we see these long filaments, we see dense cores forming along some of the filaments, and that then sets, we think, the initial conditions for star clusters. We could then take a more idealized simulation of a star cluster, so just following the gravity of the orbits. This is work with one of the PhD students, Juan Farias at Chalmers, of basically following the orbits of stars as they are born gradually from such a system. But here we don't follow the gas, we would just follow the stars orbiting, and they feel each other's collective gravity. So in fact, the more massive stars tend to settle into the center of the cluster, and the lower mass stars tend to escape. So those are examples of simulations that we're doing. But as you can see, they're often very complicated, so now we need to test these with observations. Now, this is the electromagnetic spectrum, and this rainbow is the visible part of the spectrum we see with our eyes. It's only a very small part of the spectrum. We really want to gain all the information we can across the spectrum, and to do that then we will often have to leave the ground or maybe go into space to access certain parts of the spectrum. Here's the radio observatory at Onsala, so just about 40 kilometers south of Gothenburg on a typical cloudy day here. That's okay for radio observations. You can see through the clouds. So there are several telescopes that are doing that kind of work. But often we need to see at wavelengths which the clouds block. And so then we can go to high mountains, like in the Atacama Desert. The ALMA telescope has been placed at 5,000 meters in Chilean desert here, so at a high enough place that they like to give oxygen to the people working here, not to tourist like me. But so you can't really run around too much here because it's so high up. But in the background are about 60, more than 60 12-meter dishes, which are working as one telescope, an interferometer, to see fine details. You can see there's a big bus here, so you can see the scale. So we use this facility to look at molecules and molecular ions. This is actually nitrogen, two nitrogen atoms with deuterium, that's a heavy hydrogen with a one ionized charge. So it's a particular molecule which we think traces the very early stages of star formation. And what's shown in this little movie here is a map, so position and position on the sky, 2 coordinates. But because of the Doppler effect, we also can measure how fast this gas is moving. So this third axis here is velocity. So we get a 3-dimensional picture, but only 2 dimensions are space. One is the velocity. And that helps us test this theory of cores. So this object here is, we think, an example of a massive core that's the very beginning of this cartoon sequence of evolution. Now, to see the later stages, that's when the star is formed and getting quite warm, we need to look at the infrared part of the spectrum. Now, to do that, we often go even higher. So even from the highest mountains, the atmosphere can still block a lot of that infrared radiation. But there's a telescope facility, Sofia, where they've put a 2.8 meter telescope in the back of the 747, and in flight this door will open. So it flies a bit higher than commercial airliners to get above most of the atmosphere, and then it can observe objects at parts of the spectrum not available from the ground. So we use this a lot in our research group. We have been for a number of years. Each flight then is about 8 to 10 hours at night, and then the plane takes off from California and is sort of, the mission is planned almost like a space mission. It's run by NASA. So there'll be an operation for each flight here. And there's a flight planning. The plane takes off from Southern California. It will do various flight legs. You see the telescope points out the side. It cannot, to shift from side to side, the plane itself has to turn. The telescope can point up and down a little bit, but not side to side. So if you want to look at a particular object, the plane has to be flying in a certain direction, and typically for an hour or two, then it has to turn, because it eventually has to come back and land after, well, in this case, about 9.5 hours, with observations carried out over about 8 hours. And so we might get 1 hour or 2 hours on a particular flight, for example. So we use this a lot, this Sofia Stratospheric Observatory for Infrared Astronomy partnership between NASA and the German Space Agency. It's an old 747, so inside, in fact, there are things that you might be concerned about. So not all the panels are on the walls here, but it's apparently safe. I was a little concerned by this aging electronics, which needed this fan to be cooled. Apparently that, again, was all part of procedure. You have to bring your own food, and there's no beer or wine on the plane. But anyway, you fly all night, and maybe on 1 or 2 hours of the flight, in the back here behind here is the telescope, and there's a camera on this bulkhead here, and this is actually taking this infrared observations. And so this allows us to see at wavelengths that we wouldn't normally be able to access. So in particular, this is an image at about 37 microns of a star which is forming. And when we look at it at different wavelengths, we see this particular shape, which actually tests this cartoon here of the late stage when we have the disk and these outflows. So it's testing this, again, this theoretical idea, but in this case for massive stars. We use a lot of space telescopes. Sometimes even Sofia is not good enough, so we need to really get above the atmosphere, certain parts of the infrared or the ultraviolet, or if you want to do very careful, precise photometry and position measurements, then you go to space, or the X-rays, for example. And then the next big space telescope, the James Webb Space Telescope, we hope will launch in October this year. That will be a 6.5 meter segmented dish, really the successor to Hubble. So that's the next frontier. Here's some examples of work with the Hubble Space Telescope, looking at star clusters. There are a few thousand stars here. And because of the precise position that's going to be measured from a space telescope, we've taken 2 pictures here of the star cluster a few years apart. And so by analyzing these positions, we actually aim to see the stars moving in time to see perhaps global collapse or expansion of the star cluster. Okay, let me briefly mention work then at the very early universe. So Big Bang happened 13.8 billion years ago. We have this very smooth initial state, and gravity is pulling material together, we think mostly by dark matter, which leads to collapse. And then stars start forming a few 100 million years after the Big Bang. This process has been put into simulations, not from our group, this is from the illustrious collaboration. So what you're seeing here is the dark matter, which only feels gravity and is collapsed into filaments and sort of structures that are actually similar to what we saw in our previous simulations, but now on a very different scale. So whole galaxies will form in these dark matter halos. This simulation also has the hydrogen and helium gas, and as it cools, loses its thermal pressure, it can begin to collapse into these dark matter halos. So the theory we're actually working on now is related to the very first dark matter halos. This dark matter, we don't really know what it is, but one idea is it's actually a new kind of particle, a weakly interacting massive particle, a WIMP, which is something like a neutrino, but just more massive. And this WIMP dark matter may annihilate with itself and produce gamma rays at a very slow rate, but enough to actually change how stars form from the gas. So that's the theory we're working on now, which aims to predict that basically all of these supermassive black holes form from these very first WIMP dark matter halos. And this is something that we're very excited about. You may know, in fact, the Nobel Prize was awarded for discovery of or confirmation of a very massive object in the center of our galaxy. So that's to Andrea Ghez and Reinhard Genzel. Looking at the orbits of stars in our Milky Way, we know there's a 4 million solar mass black hole in the center of our galaxy, but no one really knows where it came from. All massive galaxies, like elliptical galaxies, also have massive black holes in the center. They produce these powerful jets. But again, nobody really knows where these black holes come from. So this theory, it aims to explain where they come from by linking them to the very first stars, so that these black holes, both in our galaxy and in the Virgo cluster here, would have formed we're predicting, very soon after the Big Bang from these dark matter halos. Okay, my last few minutes then, I'll tell you a little bit about the super Earths. So it's a very exciting time for planet formation. The ALMA telescope has enough resolution to see these disks. So these are gas and dust supported by angular momentum around a young star, and these gaps may be caused by planets. Another way to see planets is when they orbit in front of the star. There's a slight shadow cast, and that causes the light to go down a little bit. Occasionally, you can see this. If this is a special date, I was sailing in Alaska here and looked up at the sun and happened to catch this little dot here, which is Venus crossing across the disk of the sun. So this is a transit of a planet in our solar system, Venus going in front of our star, the sun. The same process can happen. We can happen to catch exoplanets crossing in front of their host star. So the Kepler Space Telescope in particular looked at thousands, hundreds of thousands of stars in our galaxy and occasionally saw shadows. So in fact, has found thousands of planets now, about 10 years ago. So we now know about 4,000 exoplanet systems. And these exoplanets tend to be very close to their star. So this shows you the locations on this axis here. The Earth would be at 1 astronomical unit. Most planets found by this method are much closer in, maybe 10% of that distance. And the masses then are similar, or perhaps a bit more massive than the Earth. And these super Earths, we call them, are very important. So many of them may have conditions that allow water to be liquid. because they're orbiting quite faint stars. And this particular system, Kepler-62, is around quite a faint K star, and it has 5 planets in here. 2 of them are in this green zone here where water would be liquid. We call that the habitable zone. And we now know then, because these planets are so common, that 1 in 10 stars like the Sun has a rocky planet in its habitable zone. So these habitable environments are very common. So what we're working on is, where do these super-Earths come from? How do they form? There are 2 different ideas. The standard idea is that they form in the outer part of the disk and then migrate. So they drift inwards and are somehow stopped in the inner zone. The theory we're working on is quite different. So it involves the disk, but now we drag in the dust grains and pebbles into the inner zone, and we form the planets sequentially from rings of pebbles at this location. So it's quite a different theory. And we're again quite excited about that, because it aims to predict how common and the nature of these super-Earths. So that's a summary of the kind of work we're doing. I just point out one day we hope to get to the most complex systems, a theory for the origin of life. All we know in the case of the Earth is that life, there's evidence for life very early on. The Earth formed 4.6 billion years ago, along with the Sun. The earliest evidence for life goes back to about 4 billion years. So very quickly, under pretty harsh conditions, simple life developed. But it took about most of this time as a single-celled life. And only quite recently, within the last billion years, do we have multicellular organisms, and of course, relatively intelligent life, only quite recently. And these are the kinds of processes that must be involved. So we need to synthesize the right kind of chemicals. But as we've seen, that can happen already in space before the star forms. For biological reactions, we're going to need to concentrate them. So we need some means of forming something like cells. So that can involve fatty acids that repel water. They naturally self-assemble into globules that are cells, and then because of fusion, certain species can concentrate and start to have biological reactions, biochemical reactions. Of course, we need replication, so probably RNA is, we think, is one of a good candidate for the first replicators, things that make copies of themselves and then can undergo Darwinian evolution. So basically, how common does this compartmentalization process happen, and how does this replication go? That's a big goal of many research groups now. And the group we're doing at Chalmers, partnered with our group in Virginia, is called CHICO, so the Chalmers and VICO, the Virginia Initiatives on Cosmic Origins. It really aims to look at these questions with theory, computation, looking at how stars and planets are formed, using big telescopes like ALMA and Sofia to test these models. But also, actually, there's a laboratory component, so doing cosmochemistry, studying meteorites, studying astrochemical reactions in the lab to measure their reaction rates. And only through this combined effort can we even have a chance to answer some of these very difficult questions. How common is life in the universe would obviously be one of the big ones. So I'll just acknowledge people in our group and collaborators, and I'm happy to take questions.
Can you show the slide of telescopes again, please? Thank you.
Absolutely. Well, there's various different telescopes. Was it the space telescopes, or was it another slide? Which kind of telescope?
No, thank you. So I wanted just to take a deal, take a minute. So thank you very much. And Herschel. So what Herschel wants to do? So what is?
Well, Herschel is no longer. Well, Herschel is actually no longer operating. Herschel was a 3.5-meter telescope in space, looking in infrared, but it needed to be cooled. So there was there was a coolant, ran out of that coolant. So the mission lasted about 5 years and basically finished in about 2015. But it took a lot of data, which is still being analysed. We hope in the future something similar or bigger will go up again. The James Webb will not work at these wavelengths, and it doesn't have that coolant, so it uses this sun shield to cool down to quite low temperatures, but not as low as achieved with actual cooling.
Yes. Did you heard about that? Roger Penrose talked about that the universe has an origin before the Big Bang. That the universe actually existed before the Big Bang. Or time was existed.
I'm not quite sure
Did you heard about that?
But Penrose is receiving the Nobel Prize, or just received it for his work on black holes. So he has certain ideas about the universe before the Big Bang, and they may be true. They're a little hard to test. It's impossible to test at the moment, but certainly interesting ideas.
Yes, because his student Stephen Hawking, I think he's not believed that the universe exists before the Big Bang, but Roger Penrose is saying now it's actually possible. So I think it's very interesting that I want to know that, but I'm not so smart, but maybe I need more information. I don't know.
Right. Well, it's not something we're actively studying in our group. It's possible to imagine different kinds of universes where, for example, the laws of physics vary. The nature of how the forces balance and separate into these four forces could vary amongst these different universes. It could just be that our entire observable universe is just a small patch of a much larger universe where the laws of physics, in fact, vary. But as I say, that's a little hard to know, since we're basically limited by what we can see in our current volume. Within that volume, this 14 billion light years, there's no evidence that the laws of physics are different on one side of the universe than the other. The only thing that's globally changing, we think, is this strength of the cosmic acceleration. So that seems to be increasing now in time, but there's no evidence that if you go to different locations in the universe spatially, that the laws of physics are changed. People are trying to test that, but no evidence yet. Great. Are there any other questions?
What do you think that the gravitational waves can teach us? What can they say about the universe?
Right, so gravitational waves is another way of studying the universe, not using the electromagnetic spectrum, so using spectrum of gravitational waves propagating through space, also at the speed of light. So in principle, that can tell us many things. It is already telling us a number of interesting things. The gravitational waves that have been seen are from when you have two masses orbiting, very high masses orbiting fast. That's a situation that produces gravitational waves. In fact, that removes angular momentum from the orbit and allows, say, two black holes, or a black hole and a neutron star, or two neutron stars to eventually merge together, because gravitational waves take away the angular momentum. So what has been seen are mostly merging black holes. So typically we think these are black holes produced when a massive star, originally 100 times the mass of the sun, explodes as a supernova, leaves behind a black hole that could be 10 or 20 or 40 times the mass of the sun, roughly that kind of level. Occasionally it'll be in a binary system where another massive star exploded as a supernova, and it also formed a black hole, and they're on close enough orbits that within the age of our universe they have merged together. And eventually become one black hole, and in that process, a big burst of gravitational waves is released. Those events have been seen, quite a few events now. So that tells us about what kind of black holes are out there, tells us how common that process is happening. So it's very interesting from the point of view of massive stars, and it's the end point of some massive stars. They're also looking for supermassive black holes. So the ones in the centers of the galaxies, if two galaxies merge together, then you could imagine million solar mass or billion solar mass black holes merging together. You can also imagine stars merging with a big black hole. So the different situations. Those supermassive black holes have not yet been seen. The telescopes are not good enough. They need to see lower frequency gravitational waves. In the future, there'll be a space interferometer with lasers, the LISA mission, that will find such things, we hope. And then gravitational waves finally can also probe beyond the cosmic microwave background. So that glow of the Big Bang that I showed, which is emitted a few 100,000 years after the Big Bang, we can't see beyond that with the electromagnetic radiation. But gravitational waves can penetrate much earlier in time. So they're very faint, but through studying gravitational waves, we may be able to see the very early stages of the universe, much earlier than 1 second after the Big Bang. And that, of course, will be very interesting to know, if there are other kinds of universes, or if there's something special, very special happening at that time. Great. I hope that if other people have questions, we'd like to give them a chance. I don't know if there's a need to moderate, but perhaps Julia can moderate the questions now.
Yeah, sure. So if you have any question, you can either just write them in the chat or say them out loud, whichever you prefer. So do we have anyone who wants to raise their hand?
So, did you think the Big Bang happened because of two parallel universes colliding to each other, or something like that?
No, not particularly. I don't really have an opinion on how the Big Bang happened. It's not something I'm particularly working on. It's, as I say, it's a little. I'm mostly concerned with theories that we can test directly. Steinhardt's theories on colliding brains are one such thing. They're interesting as an origin for the Big Bang, but until they make a testable prediction, it becomes a little bit difficult. So I have a passing interest in them, but at the moment, I would say they're at the speculative level. So, if they can make a prediction for the kind of pattern we see in the microwave background, or maybe the spectrum of gravitational waves, but at the moment, it's a little hard to know. Okay.
I have a question about the percentages you had about the matter in the universe,
Sure.
like the dark energy and the dark matter. How can we know that? Or yeah, exactly that one.
Right. Right. So percentages. Yeah, this is a good question. So it turns out there's a certain amount. First of all, energy and mass are equivalent. Okay, so that's one of Einstein's results. So when we talk about energy and mass, it's all the same here, the same big pie. And there is a critical mass energy density in the universe to cause the geometry of the universe to be flat. So that relates also to general relativity and the expansion of the universe. In the simple form, if there's only matter with its gravity decelerating the expansion of the universe, if you have a certain amount of mass, then there's just enough mass density in the universe to allow expansion to continue forever, but gradually getting more and more slowly. If you had a little bit more mass than that, eventually the expansion would stop and reverse, and we'd have a big crunch at the end. If there's less than that, the expansion just coasts forever. There's good evidence that from the microwave background that we live in a flat universe, which gives us tells us there's a certain amount of mass energy density in the universe. So then, as a proportion of that, we can sort of try and count how much hydrogen and helium and other elements we see. It's mostly in the form of hydrogen and helium. And there are different ways to do that, counting galaxies and measuring how much mass they have and surveying the intergalactic medium. But also, the amount of mass that we have tells us, it also tells us about nuclear fusion in the early universe. So one piece of evidence for the Big Bang is that in the very first few minutes, it was hot enough for fusion of hydrogen into helium. Now, how much hydrogen is fused into helium depends on this percentage. So if you have more than 4%, that means you have a higher density of hydrogen, and you would actually fuse more of it to helium. We see about 23% helium everywhere, and that's basically coming from fusion just after the Big Bang, within the first 3 minutes. The fact it's 23% helium and not 27% helium and not 17% helium tells us that this amount of matter has to be in this level of about 4%. So that's one estimate. The amount of structure we see, the number of galaxies, and those, if you look in a volume of space, the kinds of galaxies we see, that also tells us how much mass is collapsing. And this is strong evidence for the presence of dark matter. So we actually, for a long time, it was known we need some extra mass. Otherwise, with just this amount of mass, it would be very difficult to form galaxies. And then over the time as well, even within our own galaxy, we see the orbits of stars going around. We know that there's not enough mass in normal matter to control those orbits. So that's also evidence for dark matter. So there's multiple pieces of evidence for dark matter from gravitational influence at about this level. Now, so for a long time, we thought maybe this was it. So we won't have enough mass density to close the universe. But then about 20 years ago, just over 20 years ago, we noticed, in fact, the universe was accelerating due to some energy field. And the energy density of that energy field, now called dark energy, has, from the latest measurements, enough to really reach this 100%. So, there are error bars here, but it looks pretty good that things add up to about 100% of the critical density, and there's no way dark matter and normal matter can do it. There's a lot of reasons to think we should be very close to 100%, and this dark energy certainly fits the bill to make up the rest here. This is the situation today. Just after the Big Bang, it would have been mostly, these percentages would have been different. The influence of dark energy would have been much smaller. But this is the situation today, 14 billion years after the Big Bang. So hopefully that...
Why would the dark matter or the dark energy be less, like the percentage of the dark energy? Or...
Right. Well, this dark energy is related to an energy field that depends on the volume of space, and the universe is expanding, and you can think of it as the expansion of space. You shouldn't think of it as the universe expanding into something, but you can think of the typical space between galaxies, for example, is getting bigger. So the densities are getting lower, and this dark energy really just depends on that volume, whereas the mass, the equivalent mass energy density is diluted by more volume. So this is just gradually getting less significant over time, and it's basically as a function, that's the cause of it. So you can think of this dark energy as a constant. It's also known as the cosmological constant. It just depends on the volume of space. And as that volume increases, it just becomes more and more important relative to the matter contribution, which is being diluted by that greater volume. And now this dark energy, because it causes acceleration, is even causing this expansion to accelerate, and these proportions will shrink here at a faster and faster rate as the universe continues.
Do you think we're living on the hologram?
In the hologram, well, again, these relate to some of these quite speculative theories of extra dimensions and so on, which are interesting, but I don't have a strong opinion one way or another. One reason they think gravity is so weak is that it is propagating through more than just the 3 spatial dimensions and the one of time, but also basically propagating through maybe as much as 10 or 11 dimensions. And because it has to work in all those extra dimensions, it's much weaker than the other forces, like electromagnetism and the nuclear forces, which are confined to the 3 dimensions, so-called membranes or brains. So it's certainly an interesting idea. It relates to string theory. Certainly one of the leading ideas. It has been a leading idea for many years, but again, it's struggling to make definitive predictions that can be tested. So I'd say it's hopefully they'll be able to make some predictions that we can test observationally to do that. One prediction is maybe the strength of gravity and how it scales with distance will change on very small scales. So there are experiments are looking at that. Maybe it will change on very large scales. I mean, not everyone is so keen on this dark matter. So there are ideas of modified theories of gravity, which would not require dark matter, but just change the strength of gravity on large scale. Those, I'd say, are interesting theories, but not supported by most of the data at the moment. So that they have work to do to explain certain features we see. But it's true, we've never directly seen the dark matter yet, and that's why there's a lot of experiments going on at CERN to try and find it, but also direct detection experiments and astrophysical experiments.
How can we know that the universe is going to change phase?
Going to change what, sorry?
Phase.
Change phase?
Phase, not phase, but phase. Not from. Like water have 3 phases. I mean, matter has 3 phases: plasma, solid, liquid. This universe is going to. Yeah.
So those phases you refer to exist even within the galaxy, and there are multiple. Things are mostly gas, and that gas can be in the plasma, so ionized or neutral or in molecular form. But within the galaxy, we have normal matter, hydrogen, different phases. But I don't think you refer to that when you talk about the whole universe.
Yes. I mean, the universe can also have a phase, but how we can know that it's going to change phase? Maybe in the future.
You're talking about phase, which is including forces. So this is something that happened very early in the universe, we think. And it's true then that this kind of phase transition, may originate the expansion, the accelerated expansion of the universe. In fact, we think there was a very rapid expansion early on, the inflationary phase, within the first less than a microsecond, which then led to our observable universe. So that relates to this multiverse theory. So you could imagine a much larger universe where different parts undergo the phase transition at different rates, and we happen to live in just one part, and then the physical constants, the laws of physics, may settle down to certain values, which could be quite random within, depending how the symmetry is broken between these forces. So I recommend Martin Rees's book, 6 Magic Numbers, which describe different possibilities for how that phase transition would then lead to the universe today. Life as we know it requires certain combinations. So, we require gravity to be much weaker than these other forces, for example. We require the hydrogen, the ratio of the electromagnetic forces to the nuclear to have certain values. Otherwise, we wouldn't have stable atoms, and we wouldn't be able to do nuclear fusion. So there's certain combinations which are required to actually have stars and planets and thus probably life. And so one can imagine a very vast multiverse with lots of different phase transitions happening, lots of different possible universes, but only ones, very rare ones, with certain combinations of these force strengths, allowing life to develop. So again, that's an interesting idea known as the anthropic principle. It's a little hard to make predictions with it. Of course, we live in a universe allowing life because we are alive, so it's a little circular in that sense. But still, an interesting philosophical idea, I would say.